Good morning. Welcome to our presentation on credit card fraud detection using machine learning. So our team members are Krispa, myself, Surya Gayatri and Hema. So coming to the introduction, uh, next slide please. So coming to our introduction, our project addresses the significant challenges posed by fraudulent activities in credit card transaction, both online and offline. With the growing dependence on the internet and the rise in physical fraud, robust detection systems have become essential. By leveraging machine learning, we aim to identify anomalies and fraudulent behavior with greater accuracy. Our main focus here is on effectively tackling the issue of imbalanced data sets and also optimizing detection through advanced metrics and techniques. We will discuss the problems, objectives, and also the strategies used to implement and evaluate various machine learning models. So here, credit card fraud is a critical issue affecting both physical and digital transactions. As online and offline fraud continues to rise, effective detection and mechanisms have become essential. Here, machine learning plays a pivotal role in identifying fraudulent activities within large data sets by detecting anomalies efficiently. Next, next slide. So coming to the problem definition, the problem is mainly involved in terms of the goal and challenges associated with detecting fraud. Here our objective is to detect fraudulent credit card transaction using machine learning techniques. The challenges involved here is the first one is the imbalanced data set. So fraudulent transaction make up only like 0.172% of the data. This imbalance complicates model training and also evaluation. Next one is the metrics. So specialized evaluation metrics like APRC, that is area under the precision recall curve, and also AUC and ROC are required to access the performance effectively. Next one is the dataset overview. So the data contains anomalized and also PCA transport features to protect privacy, and the response variable is labeled as follows. Class 1 basically indicates the fraudulent transaction, and class 0 indicates the non-fraudulent transaction. So here our goal is to accurately identify fraudulent transaction while minimizing both false positives as well as false negatives. Next one is next slide. So next one is the architecture overview. So the architecture overview includes the following components. First one is the data input. So basically it represents the collection of raw transaction data, including various features relevant to credit card transaction. Next one is the data pre-processing. It involves cleaning and preparing the data, including handling missing values, normalization, and also pre-state transformation. Next one is splitting the data like into trained. So it refers to the process of dividing the data set into two distinct subsets for the purpose of model training and evaluation. The basically training phase describes the process of training the models on the pre-processed data set, including data set splitting and also cross validation. Next one is model selection. So it outlines the choice of machine learning algorithms used for fraud detection, such as logistic regression, naive-Bayes, isolation forest, and also local outlier factor. So here, logistic regression and also naive-Bayes comes under the category of supervised machine learning models, and isolation forest and local outlier factor comes under unsupervised machine learning models. Next one is the model evaluation. It basically assesses the model's performance using metrics suitable for imbalanced data sets like APRC and also AUC ROC curves. Next slide. So coming to the data set, so the data set is sourced from Kaggle credit card fraud detection data set, which contains anomalized transaction data from European card holders over 2 days, European card holders. And here the key statistics are like total transactions is about like uh, 2,84,804, and also fraudulent transaction is like 492, which is like 0.172% of the total data. And here the data set is highly imbalanced, like with fraudulent transaction forming a very small fraction of the total, of the total. And here the PCR transformed features. So there are these are the primary variables like after dimensionality reduction. And also here there are untransformed features untransformed features mainly like includes the time, that is the transaction timestamp, and also the amount, that is the transaction amount. Next one is a target variable. So as earlier said, class 1. So class 1 like basically refers to fraud, and also the class value of 0 refers to the non-fraud. And here next one is the data loading and pre-processing. So here the data set is loaded into a data structure for analysis, and also null values are checked and the summary statistics are calculated to ensure data integrity. And next one is the imbalance analysis. So like a significant challenge is the imbalance in the data set, and also visualization techniques like count plots help illustrate the disparity between like fraud and non-fraud cases. Next one is the feature engineering. So here like important features such as amount and time are analyzed, and transformations binning are applied for like a better interruptibility. And also correlation metrics also helps identify relationships among features. Next one is the data set splitting. So here the data is like divided into training and testing sets. And also here the shuffling ensures like variability and also avoid order bias. So here uh, the architecture is basically designed to handle challenges posed by imbalanced data and anomalized features, ensuring an effective foundation for building, training and testing machine learning models. So this setup enables accurate fraud detection while minimizing false positives and negatives.
Good morning, sir. We'll be looking at how the model selections that we have taken, the algorithms that we have taken are logistic regression and naive, which is part of supervised learning. In logistic regression, we use a statistical method to predict the probability of a binary outcome, and in turn, it maps the input features to a probability using a sigmoid function. So, which is well suited for us to linearly separate which is linearly separable data, limiting it by its linear assumptions and sensitivity to the outliers. Outliers basically mean the decision boundary that we've been using there. And coming to the naive Bayes, it is again a probabilistic classification algorithm based on the Bayes theorem. And assuming that all the features given in the dataset are independent, and which can be a strong assumption. It is very simple and efficient, especially when we're trying to do a text classification. Here, we're trying to do a numerical classification. So it is also helping here in our imbalanced data set. Next, to the unsupervised learning, we have used isolation forest and local outlier factor. An isolation forest is basically it's an unsupervised anomaly detection method, which is very suitable for our anomaly fraud detection. And it isolates the anomalies by randomly selecting the features and splitting the data. It's again very efficient and effective for high dimensional data like ours with 2 lakh plus data sets of the transaction data. And it is sensitive to the parameter tuning, which we'll be doing. And the other algorithm that we've used is local outlier factor, which is a density-based outlier detection method. It calculates the local density deviation of a data point. It is robust to the noise and effective for complex data distributions. And at times when the data is more than what we have, it can be computationally expensive. But here we could achieve, we could work out with the LOF algorithm. Now we'll be looking at how the data pre-processing is working through the Jupyter Code notebook that we have implemented. We have imported all the required Python libraries like the pandas, the NumPy, Seaborn, which are all used for visualization, the data structuring, and for predicting, for outlining the scores, the F1 score, and the performance, the precision, accuracy. We have imported all the required libraries. Now to the data pre-processing. In the data pre-processing, we are doing a PCA, basically principal component analysis, so that we can narrow down. We are doing a reduction there so that the data reduction is done, and we could take what features and columns that we require from the data set. So the data set is basically a CSV file, which is named as credit card. We're taking a backup of it. And the data frame here is a data structure where we have the columns and rows, which are the features here. And the data frame dot shape gives us the number of rows and number of columns. Number of rows is the number of transactions. Number of columns is the features that are associated with each transaction. And it also, the data dot is null values dot any is finding out if there's any empty data in the whole data set. When we say data frame describe, it describes it gives a description about the data set, which can be the number of transactions, which is the count. It can calculate the mean, the standard deviation, the minimum value which is available, minimum amount here in this case, and 25%, 50%, 75%. So these are the boundaries. So 25% means that one person, if the time is like 54,207, so which means that is the that is taking the lower bound, and 50% means they are on the line, they are on that boundary, and 75% means they are on the upper boundary, and similarly the max. Now we are checking the frequency of frauds. So to check the frequency of frauds, we are using the Seaborn library, which is the SNS, and we are trying to plot the count. So here the x-axis will have the number of transactions, which is the count, and the y-axis has the count, which is the number of transactions, and the x-axis here is the class. So the class here defines as 0 and 1, which means 0 being there is no fraud, and 1 being that there is some fraudulent transaction being done. Coming down, here we are trying to, so from the above statistics, that was a histogram that we just saw. So from that histogram, we are trying, since it's very imbalanced, we're not able to see how many number of transaction has a fraud data set, how many number of fraud transactions are there. We're trying to reduce that imbalance data set by reducing the by using the outlier fraction and bringing it down. Now, from that fraud and valid transactions, we are trying to assign what are fraud, what are normal. So when it comes to fraud, we get that the count is 492 transactions of fraud transactions, and we are calculating. We have a description of that data frame here of the classification as fraud. The next is the normal classification, where we have 284,315 transactions as non-fraud, which is like a normal transaction. So genuine, and it's a valid transaction. So we are taking the description of that normal transactions there. And here again, we have the upper boundary and the lower boundary being plotted. Coming down, we are plotting the heat map here by putting up the features, and this is the heat map, as you can see. Can we scroll down? Now, from this, we are trying to get into the disk plot. So this disk plot is going to put in the density distribution plot, where we are putting the data of considering the feature as amount. So here, the two features that we're considering is the amount and the time. So which would which would help us to find out and narrow down which transaction took how long, and does that lead to a fraud transaction. So here, these amounts are ranging from no transactions, that is absolute zero, and to about say 25,000 and above. And the densities are plotted on the y-axis. Since this is very imbalanced again, we are trying to use the binning concept where we are trying to formulate the ranges of these amount into separate bins. So these separate, we're using the amount bins in the data frame. To make these bins, we have put the labels here and coming down. Yeah, so the ranges here for each bin is set to 0 to say 2,854, which would be the first bin. And so from 2,854 to the next, which is 5,709 as a second bin. So from the amounts, these bins are the amount bins. So the transactions done between that particular range is set, and we're trying to find out the counts in that particular bins. So that's what is depicted. So the most of the transactions lies in the range, the first bin, the amount bin being from 0 to 2,854 rupees. Now we are again plotting the histogram with this amount bins and the y-axis having the count. Again, it's so vast that all of them lie in the first bin, amount bin, and that range is so high. So we are reducing the count so that we could see if there is any other transaction, the other transaction that lies between the other amount bins. As you can see, it is the orange shows the orange histogram shows the amount lying in the range between 2,654 to 5,709, and so the green and red and the purple is again displayed there. And we are using in order to predict whether this classified credit card transactions are fraud or non-fraud. We're using some machine learning models, as we discussed, the model selection that we have done. Before that, we'll be doing a one-hot encoding for this amount bins. So one-hot encoding would classify that the amount bins that lie in the range 0 to 2,854 as classified as 1, and the others are 0. So this is just like the numerical from the statistics, we have assigned the values as 1 for that particular bin.
I am Hema, and I'm going to be taking over the explanation of the code. Next, we are breaking the data set into training and testing. What the train test split function does is it divides the data set into training and testing subsets. So here the input features X and the target variable Y are separated. The function randomly splits 70% of the data into the training set, which is X train and Y train, and 30% of it into the testing set, which is X test and Y test. So here the parameters in this code, which states random state is equal to 42, ensures the reproducibility by fixing the random seed. Then test size, which is equal to 0.3, specifies that 30% of the data goes inside the test set, and shuffle equal to true. This means that the data is shuffled before splitting, so that this avoids bias while splitting. So here we can see that the training set space has this many numbers of features, and these would be the target labels. And similarly, this is for the test set. Now we're applying the logistic regression, NaiveBayes, which are the classification algorithms, and the other two, isolation forest and local outlier algorithm, would be unsupervised algorithms. And these are some of the metrics that we will be using. Now coming back to the slides. So this is the code for logistic regression. We are splitting the, we're training the trained data set and we're putting it inside the logistic regression. These are the confusion matrix and the ROC curve that we have observed. So here in the confusion matrix, we can see that there are 84 cases of true positives. This means that 84 cases of fraud were correctly identified, and the number of false negative is 52 cases. This means that 52 cases of fraud were missing and were classified as not fraud. And similarly, there are 32 cases of false positives, which means 32 cases were incorrectly classified as fraud. And there are 85,275 cases which were incorrectly classified as not fraud. And also in the classification report, we can see that the accuracy is 99.90. And for prediction of fraud, which is class 1, the precision is 72%, and that means that out of all cases predicted, 72% were actually fraud. The recall is 0.62. This means that only 62% of actual fraud cases were identified correctly. The F1 score here is 0.67, which indicates a moderate balance between precision and recall. So here the macro average precision is equal to 0.86, recall is equal to 0.81, F1 score is equal to 0.83. So the averages across both classes, so this treats them equally. The weighted average in the weighted average, precision, recall, and F1 score are equal to 1. This means that because of the weighted by class distribution, it is dominated by the non-fraud classes due to the imbalance of the data set. So here we can see that the classifier performs very well for the majority class, but struggles a bit with identifying the fraud classes because of imbalance issue. But the precision is still really good, even though the recall is a bit lower. The F1 score and recall are still very good. So looking at the ROC curve plots the true positive rate against the false positive rate. So this is a curve that approaches the top left corner and indicates better performance as it signifies high recall and low false positives. Here the area under the curve is 0.923, which is an excellent score, showing that the model has a strong ability to separate the two classes. In the next slide, here we are fitting the naive Bayes algorithm, and we can see that the confusion matrix here is also similar to the logistic one, but the only difference is here the recall is a bit better, as we can see. That the recall here is 0.66. The precision is 14% and the recall is 0.66. F1 score is 0.23. Coming to the next slide. This is for the isolation forests. These are the unsupervised algorithms. We have fitted the whole data set into these algorithms. So in the isolation forest, we can see that the precision is 0.16. Recall F1 score are also 0.16. This algorithm doesn't perform as well as the classifiers, but still has a pretty good precision and recall. The accuracy score is 0.997, which is also pretty good. The next algorithm that we have used is local outlier factor algorithm. Here the precision, recall, and F1 score are pretty low, which is 0.02. This is a confusion matrix, as we can see. Now these are the results and discussion. This slide is a comparison between the logistic regression and the naive Bayes. So the inferences that we can see here are that logistic regression performs better in terms of precision, F1 score, and AUC ROC curve. It balances the false positives and false negatives better. Naive Bayes slightly has a better recall, which means that it detects more actual fraud cases. It also has high false positive result in poor decision precision. So these are results and discussions of the isolation forest versus the local outlier factor. Looking at this, we can say that the isolation forest performed better in determining fraud cases with an F1 score of 20% compared to LOF's negligible performance. While comparing error, precision, and recall for these models, the isolation forest performs much better than the LOF, as we can see that the detection of fraud cases is around 20%